Assalamualaikum and good day to all of you. So today I will discuss chapter 3, three-phase system. So these are the content for chapter 3. So in this chapter I will divide into two parts. Part A will cover introduction, three-phase generation, three-phase circuit, definition phase and line voltage and phase and line currents. The last subtopic for part A is voltage and current in star-connected system. And after part A, I will continue with part B, voltage and current in delta-connected system, power in three-phase circuit. The last subtopic is measurement of power in three-phase system in practical. So these are the learning outcome for this chapter. You have to understand the generation of three-phase, familiar with delta and star connection system, able to calculate voltage in both connection, understand the relationship between line and phase value, able to calculate power in three-phase system. Finally, you have to familiar with the measurement of power. So let's start with part A. So this is an example of power system in Malaysia. So this is the complete system. So here, this is the generation division. And then you have transmission division. Okay, for transmission division, the voltage level here is 132 kV, 275 kV, and then the highest voltage level is 500 kV. So this is the voltage of transmission division in Malaysia. So and then after that, before it transmit to distribution division, so the voltage level will be stepped down by the transformer. So for example, from 132, it will step down here to 333 kV. So the distribution level, voltage level is 33 kV, and then it will step down to 240 or 415 volt, depend on single phase or three phase. So this is the real picture for generation, division, transmission, and then distribution. So at the transmission division, this one we call transmission tower. So at transmission tower, you have three phases. For example, I assume this one is red phase, and then yellow phase, and blue phase. Okay, so normally at the transmission tower, we have one plate that show the orientation of your phases. And then the upper one is neutral wire. Okay, so let's discuss on advantages of three-phase system over single-phase supply. So for a given amount of power transmitted, the three-phase system requires conductor with a smaller cross-sectional area. It means you can save the copper and aluminium, and then finally the original installation cost is less compared to single phase. And then for three phase, it has two voltage. So the first one, you can tap your supply at phase voltage, or also you can tap the phase supply at line voltage. So a 4-wire system is used when the load is not balanced. So the diagram of connection is follow. So for example, you want to tap at line voltage, so you tap directly from red phase or yellow phase or blue phase. Also, you can tap at the phase voltage, where you tap between red and neutral, or yellow and neutral, or blue and neutral. Okay, the next advantages is the three-phase motor are very robust, cheap, generally small, and also provide a steady output, and then require little maintenance compared single-phase motor. Okay, next is single-phase induction motor is not self-starting, but three-phase system is self-starting. Okay, and then the last advantages is for the same power output, the three-phase generator costs less and then produce uniform power, and then less vibration and noise compared to single-phase generator. Okay, so this is the three-phase generation. So the basic principle is same with single-phase, but for three-phase, you have three set of this coil. So for example, this one for red phase. So you have another two for yellow and blue. Okay, so this is the waveform of voltage for three phase. So you have waveform, the red one waveform for red phase, the blue one for yellow, and the black one is for blue. So from the voltage waveform we have learned, we can transfer into the phasor diagram. So here is how you transfer from waveform to phasor. So you can see that the phase difference is 120. So that's why, okay, the relationship is the phase difference between red and yellow is negative 120, and then red and blue is either negative 100, negative 240 or positive 120. So from this relationship, we can produce this relationship or equation. So certain textbook use ABC instead of red, yellow, blue. So other country also use X, Y, Z. So for example, red is X, Y is Y, and B is Z. So normally in Malaysia, we use red, yellow, blue. So this is the relationship. So ERR is voltage for red phase, sin theta with the value of theta is 0 or phase angle is 0 because it starts at 0 point. And then for yellow, it starts, so it lagging. So that's why sin theta minus 120. And then for blue, it's leading. So that's why it be sin theta plus 120. Or you can write it as theta minus 240. So this relationship you have to remember. Okay, so for three-phase system, we have two sequence. The first sequence is positive sequence. So where the sequence is red, yellow, blue. Okay, normally we use positive sequence in analyze our three-phase system. Okay, so this is the phasor diagram for positive sequence, red, yellow, blue, and then this is your waveform. So this is the relationship we identified before. Okay, so how about the negative sequence? Negative sequence, the orientation of your phase is red, blue, yellow. Okay, so and then the relationship is different with positive. You can see here plus and minus is different. So normally we use positive sequence to analyze your circuit. Okay, so let's try this example. So assume the system is balanced and sequence is red, yellow, blue. So we know that it is positive sequence. Okay, so now you know that the system is positive sequence. So you can write your relationship here for your reference. So given ERR equal to 277 with 0 degree. So what is the value of EYY and EYB? So refer to this one. Okay, so E y y equal to, the magnitude is maintained. So 0 same as this one. So you can directly get the answer. Negative 120 volt. Okay, and then for EBB, so equal to 277. Okay, since this is 0, so you can straightly get the answer, positive 120 volt. Okay, how about this one? Okay, so the question give you yellow phase. So find the value of voltage produced for red and blue phase. So you compare to this relationship. Okay. So E R R. So this one is already in minus 120. So you know that for ERR, the degree will be 0. Okay. And then for EBB, okay, so you can straightly get the answer is 347 with degree positive 120. So the relationship is very important here. Okay, next is the question give you the value of voltage for blue phase. Okay, so blue phase. Okay, so how to get the value of ERR? So the relationship is between red and blue is 120 plus. But if you want to get the value of ERR, so you have to inverse. So ERR equal to 120. Okay, red to blue positive. So you want to get from blue to red, so you have to minus. So 150 minus 120. Okay, you will get 120 with degree of 30 volt. Okay, how about EYY? So 120. So the relationship will be inverse, so you have to plus. So 150 plus 120. So you will get 120 to 7 volt. So this is the answer. Okay. Okay, so for three-phase circuit, it has two types. Okay, you have star or Y connection. So normally we call it a star connection. And then delta or mesh connection. So this is the diagram for star and delta connection. Okay, so connection between alternator or load. So where is the alternator? So this at the left side is alternator. Or we also can call generator. Okay, and then at the right hand side is your load. Okay. Okay, so refer to this connection, so you know that this is star connection, and then this one is delta connection, and then star delta connection, and this one is delta star connection. Okay, so star to star connection. Okay, you can see this is your red, yellow, blue phase for generator or alternator, and then this is your load. So this is the current flow for each phase. Okay, and then you have the neutral conductor. So with a neutral conductor, you're also known as four-wire system because you have four phases. Okay, so this is your neutral point. So with a balanced load, after this we learn how we can identify balanced or unbalanced load. Okay, with a balanced load, the resultant in neutral conductor is 0. So you will get current through red phase plus I yellow phase plus I blue phase equal to 0. So you can neglect the IN. Okay, so if the system don't have neutral wire, okay, it is known as three-wire star-connected system. Okay, so let's continue with the definition of star connection. So this is your generator part connected in star and also the load connected in star. So what is the line voltage? So you have two sides. Alternator normally we use in capital letters. So ERY, EYB, EBR for line voltage in star. So this is where your ERY, EYB, EBR. Okay, but for load, the phase we use small capital letter. So for load, we write it VRY, VYB, and VBR. So this is how you write or differentiate between generator and the load. Okay, how about phase voltage? So phase voltage at generator is ERN, EYN, and EBN with capital letter. But for the load, you have to write it as V, small capital letter RN, VYN, VBN for phase voltage at the load. So line current, so this is the current for red phase, yellow phase, and blue phase. Okay, so this definition is very important you to understand because this one we will use in calculating or analyze the three-phase circuit. Okay, and then the definition for delta. So this is your delta connection at the load. Okay, so line current, so because it is at the load, so this should be in small letter. So IR, IB, I yellow, I blue. So current in the line conductor, IR, IB, I yellow. And then for the phase current is IRY, so between R and yellow, red and yellow. And then IYB is between Y and B. And then IBR is between B and R. Okay, and then for delta, line voltage is equal to phase voltage. Okay, so before this, for star, line current is equal to phase current. So different with delta connection where your line voltage is equal to phase voltage. So the relationship you have to remember and understand for both delta and star system. Okay, so let's see the relationship between voltage and current in star connected system. So this is your star connected system. In order to get the relationship, so this is the proven process or step. So, okay, so first you have to apply KVL. So you have to apply KVL here. Okay, when you apply the KVL, you will get positive VRY. Okay, positive, and then plus VYN. Okay, and then minus VRN equal to 0. So this is the initial of KVL equation. and then you rearrange, you will get VRY equal to, so negative will be positive, VRN minus VYN. So that's why you get this first equation. So now assume the magnitude V for each phase voltage. So we take VRN as reference. So we write is V with theta 0 because we assume that VRN as reference. The sequence is positive sequence and the system is balanced. So you refer back to the relationship we have learned before. So you can write it as this one. So you will get the second equation. So now you substitute second equation into first equation. So this is your first equation. You substitute VRN is V theta 0 minus VYN. Okay. So this one is actually same. V times 1 is 1. So times 0 you will get 0. Okay. And then this one you change to complex number form. Okay, and then finally you will get this answer. Okay, so 1.732 is actually square root of 3. Okay, with the degree of 30 degree. So you will get, finally you will get VRY is equal to 3 VRN with 30 degree. So you apply the same step for other two KVL. So here, okay, you will get this equation, and then here you will get this equation. So you substitute second equation into this equation, you will get this formula. So the conclusion is voltage and current in star connected system. So this is actually what we want to get. So V line is equal to Z3 V phase with theta plus 30. Or you can rearrange back, you want to get V phase. So that's why V line over Z3 theta, because it is. So divide, so you have to minus 30 degree. So this is just for balance system, either in star or delta connection. Okay. So this is the formula for V line for each phase. So V line VRY equal to Z3 VRN at red phase, and then for VYB, so V at yellow phase, and then VBR is V at blue phase. So this is the formula for star connected system. And then remember, for star connected system, I line is equal to I phase. So let's try this example. So you have balanced star connected system. So how you identify either the system is balanced or not? The way is you can see that the load is same for both, for three phase. So Z impedance for Z at red phase, yellow phase, and blue phase is equal. So you can say that the system is balanced system. Okay. So if the value of impedance for each phase is different, so the system is unbalanced. So for this case, the system is balanced. Okay. So the first one, you have this diagram, your alternator, and then your load. So this is VRN. So VRN is actually your voltage at load. Okay. So the first question, determine the phase voltage. So remember, phase voltage at the load. So VRN is your phase voltage, right? So let's solve this example. Okay, phase voltage. So find the phase voltage So your phase voltage is VRN because it is at the load. VYN and VBN. Okay. So your VRN is given is 120 with theta 0. Okay, so you refer to the relationship Yn equal to 120 plus or minus. So minus 120 volt. And then for VBN, so plus, right? Plus 120 volt. Okay, so this is the step you find the phase voltage of star connected system. And then for B, the question asks you determine the line voltage. So line voltage. So line voltage is V R Y V Y B V B R. So how to determine this one? So you refer to this equation. So V line equal to sub-3 V phase theta plus 30. So you already have your V phase. So you can find your line voltage equal to sub-3. So red, so you refer to the red one. So your red phase 120, and then theta. So theta for red is 0 plus 30. So you will get 208 with theta 30 degree volt. Okay, so same step VYB. So sub 3 times 120. Okay, refer to yellow phase. So your degree is minus 120 plus 30. Okay, you will get 208 with degree of 90 minus 90 degree volt. Okay, the last one is VBR equal to sub-3 120. So refer to the phase at blue. So plus 120 plus 30. So you get 208 with degree of 150 volt. Okay, so this is how you find your line voltage. Okay, and C. Okay, show all the voltage in phasor diagram. So you, from this equation, you transfer to phasor diagram. So this one I'm not going to show you. You can try yourself. Draw phasor diagram. Okay, next question. Calculate IR. Okay, calculate current at red. Then determine I yellow and I blue by inspection. So what it mean by inspection? So IR, I yellow, I blue. Okay. By inspection, what it means is Okay, so you can find. Okay, so apply Ohm's law. V equal to IR. So I equal to V over R. So IR equal to VRN over ZRN. Okay, so refer here, your VRN is 120 degree of 0, 120 degree of 0, and then your impedance for Rn given 12 minus J9. So use your calculator, you will get 8 degree of 36.87 M. Okay, we can find yellow current in yellow and blue by inspection. You just apply the relationship same like voltage for yellow. You don't need to apply Ohm's law. So from the value you get for red phase, so you can, okay, relationship is minus 120. Same in for current and voltage for yellow phase. Okay, you will get 8 minus 83.13 M. And then for blue phase, the relationship is plus 120. So plus 120. Okay, you will get 8,156.87. Okay, so this is how you find current in red, yellow, blue by inspection. Okay, so you just apply the relationship same with the voltage, minus 120 plus 120. Okay, the last question asks you verify answer in D by direct computation. So I read IY IB by direct computation. What it means is, okay, so you already calculate IR using Ohm's law. By direct computation is you have to find I yellow using Ohm's law. So your VYN over ZYN. So you refer back to, this is VYN. Okay, 120 minus 120. Okay, over 12 minus J9. So you will get the same answer. Use your calculator. You will get the same answer as in D. Negative 83.13. Okay. So repeat the same step in find I blue. Okay, so for I blue, VBN over ZBN. So VBN is 120 plus 120, 120 plus 120 over 12 minus J9. So your answer will be same, 8,156.87 M. So this is the difference by using inspection and direct computation. So if the question did not mention with method you can use, so you can choose either by inspection or direct computation. But this one is for balance system only. So if you have unbalanced where your value of Z at the load is different, you have to use direct computation by apply Ohm's law. Okay, so I already finished for part A. So next week we will discuss on part B. Okay, so any question you can communicate with me through WhatsApp. And so that's all for part A. Thank you.